Welcome back everyone to another video in our FE Civil Preparation course, and in this video we are going to talk about soil vertical stress. In our last chapter we learned the different properties of soil and their classifications, as well as the laboratory and field tests we carry out to come up with those soil properties. In this chapter we are going to discuss the stresses caused due to the soil. Soil has its own weight. Because of that, each soil layer is causing vertical stress on the layer beneath it. This vertical stress simply equals to the weight of the soil layer above, so it makes sense that the vertical stress will be in shape of triangle that increases as we go further down. So if we considered a soil layer at a depth of 1 meter, it is under vertical stress caused by the weight of 1 meter depth of soil which is above this layer. And the weight of the soil simply equals the density multiplied by the dimensions. So if we want to calculate the stress on a unit area of 1 meter square, then we are going to multiply the density of the soil, which is gamma, by the height of the soil. So we will end up with this stress distribution shape as we can see here. If we have these two layers of soil here with H1 and H2 depths and gamma 1 and gamma 2 of soil density, the stress at the bottom of this layer, which is called sigma, will equal to gamma 1 multiplied by H1, where gamma 1 is the density of this soil and H1 is the height of this layer. While sigma 2, which is the stress at the bottom of this layer, will equal to sigma 1, which is gamma 1 multiplied by H1, in addition to the weight of this layer, which is gamma 2 multiplied by H2. So this here will be what we call the total vertical stress. However, we can see here this symbol, and this symbol, it means that the water table is at this level, so this part of the soil, it is submerged underwater. So what is the water effect? Try to imagine what happens if you are in a pool and you are trying to push a ball, for example, inside the water. Exactly, you will have resistance from the water, because the water is trying to push the ball out. It is the same force generated by the water that saves you from sinking while swimming, and this is called uplift force. The same force will exist here in the soil due to the water table. The water is trying to lift the soil up, but because the soil has higher density, it doesn't float up. However, the water is reducing the weight of the soil and reducing the stress on the lower layers of the soil. And it is calculated exactly the same way we explained soil weight. So it will be calculated also by the equation of gamma multiplied by H, where gamma is the density of the water, which is 62.4 pound per feet cube or 9.8 kilonewton per meter cube. And this force, it will be directed to up, which means it is in the negative direction. So now we have the total vertical stress and we have the pore water stress. This stress is going downward and this stress is going upward. So the effective vertical stress will equal to the total stress minus the pore water pressure. So sigma 1, it will equal to the same, the effective and the total, because there was no water here, while sigma 2, it will equal to the same sigma 2 total, but we will add here this term, which is minus gamma water multiplied by H2. Here, this is a different condition for the vertical stress. It is in case of surcharge pressure. And surcharge pressure is any vertical load on top of soil which could be due to traffic, equipment, or any other source. In this case, the soil vertical stress will be calculated exactly the same way, except that surcharge pressure will be added at each level, as we can see here. So the pressure will not start from 0 like last time, but it will start with the value of S, where S is the surcharge pressure. So now, let's have an example on this. So let's check this example. We have this soil here consisting of two layers, 5 feet depth and 10 feet depth. The first layer is sand with density of 132 pound per cubic foot, and the second layer is clay with density of 126 pound per cubic foot. We have groundwater at depth of 2 feet from the top, and we want to calculate the vertical effective pressure acting at point A, which exists in the bottom of the second layer. We have to take care that here he is asking for the vertical effective pressure, because the effective pressure we will deduct the pore water pressure, but if he was asking for the total pressure, we will not deduct the pore water pressure. So let's calculate the pressure at point A. The pressure at point A will consist of 5 feet of sand with a weight of 132 pounds per cubic foot, and in addition to 10 feet of clay with density of 126 pounds per cubic foot. And we will deduct 13 feet of water, which has a gamma of 62.4 pounds per cubic foot. So this will be the final formula, which is sigma effective at A equals 132 multiplied by 5 plus 126 multiplied by 10 minus 62.4 multiplied by 13, which will equal 1108 pounds per cubic foot, which is PSF. So the answer is B, which is 1100 PSF.